Hi, this is Smo Love True, and Tony had shared this article. It's the Technology Report, an update on nanoscale technologies for RF and microwave applications from December 2010, High Frequency Electronics, copyright 2010 Summit Technical Media, LLC. And the reason why I'm reading this is because this is actually the second time Tony has sent this over to me. Many years ago, the advent of the integrated circuit revolutionized electronics, allowing much greater complexity, speed, and performance in a small size, and at the same time dramatically lowering cost. Today, new steps in miniaturization promise another leap in capabilities at smaller size. Nanomaterials, micromachining, and other microscopic methods are beginning to reach the market in many fields, including medicine, computing, and of course electronics. In the area of wireless communications, these technologies are being pursued to achieve greater capacities in handheld platforms. The only way to put more features into limited size package is to make the circuitry smaller. In the digital realm, Moore's law has helped with the processing and memory portion of wireless devices. Nanoscale technologies are being readied to help with the basic radio performance that enables portability. According to Larry Morell, Executive Vice President of Sales and Marketing at Cavendish Kinetics, Microelectromechanical Systems, MEMS, switched capacitor devices for antenna tuning are scheduled for release in 2011. Morell notes that demand for this capacity, which is also being addressed by tunable technologies and other switching devices, is due to a rediscovery of the importance of core radio performance. The high data rates of 3G, 4G, and beyond require maximum signal-to-noise ratio communication. Solutions include improved base station performance, for instance, MIMO, smart antennas, the microcell, picocell deployments. These infrastructure improvements are costly, and so attention is being given to the handset radio. The key performance limitation in handheld devices is the antenna. Early cell phones had extendable monopoles that had relatively high efficiency, but at the quest for smaller size, embedded antennas became standard. These antennas are not only less efficient, they are susceptible to detuning by the proximity of the user's hand, famously demonstrated by the first generation iPhone. Antenna tunability allows optimization of impediments. Antenna tunability allows optimization of impedance matching to combat such degradation. Tunability also has the potential to enhance antenna sharing by the multiple services now supported in a handset. Multiband wireless, GPS, Bluetooth, Wi-Fi, broadband, DTV, and others. Morell, who is also chairman of the Tunable Components and Architectures Group of the industry organization IWPC offered some insight into the challenges of fabricating MEMS devices at costs low enough for consumer products. The primary issue is the required hermetic seal to protect the active structures from contamination. Most developmental work involved gluing two die face to face, then sealing the assembly in plastic. This method has been supplanted by either a silicon etching process developed at Bosch, or a process of built-in metallization passivated to achieve the hermetic seal. Both methods are compatible with traditional silicon wafer fabrication, which should be able to achieve cost goals.
Welcome to Pault on Power. This is a special video edition to commemorate the Global Press Media Summit that's going on right now in California. We've got a bunch of different companies, and we'll have several video reports for you guys and gals out there from the media event. And we're starting off today with Dennis Yost. He's the president and CEO of Cavendish Kinetics. And we're talking about, in this context, RF power and its power considerations for the engineer. I mean, RF is one of your most power-hungry aspects of a system, wouldn't you say, Dennis?
That's correct. If you really think about power amplifiers and running very efficiently and in their high linear region versus wasting, a lot in heat, it's one behind the screen in a cell phone. They consume more energy than anything.
Exactly, including the screen, right?
yeah, including the screen, but the lighting of the screen. But the PAs, especially LTE PAs, are very, very good hand warmers. They really can keep your hand warm in the wintertime. And part of our application is to make components, in this case, dynamically tuned capacitors, in order to improve the overall efficiency of the cell phone, both in transmit power, the efficiency of the PAs, as well as the efficiency of making sure all the power gets transmitted out of the phone and there's not a lot reflected back in.
Well, and that's a big issue, isn't it? Reflected power. If the antenna, if there's any kind of a mismatch or any problem with the antenna, you're just wasting power as heat. And it's also a problem for the system itself, isn't it?
Yeah, mismatch is one that actually wastes power. And could be a mismatch between the system and the antenna, but then the other mismatch is between the antenna and the outside world. And both mismatches have to be managed in order to have the most efficient performance. And so really making that efficiency good, that it actually has high transmission gain, really is the key to making the power amps and all that operate in their most efficient regime.
Exactly. Now, obviously we're talking about the antenna here.
Mm-hmm. Yes.
Now, when it comes to the antenna, you hear things about fractal antennas and you hear things about various tunable types of antennas. What is your approach? Where are you coming to this problem from?
So we're supporting pretty much any kind of an antenna type, but in a cell phone what ends up happening is you shrink the antenna well below the quarter wavelength of the frequency. And when you shrink it, it's not very efficient. So consequently, when the antenna is not very efficient, you have to make it very narrow band, or if you make it very wide band covering all the frequencies, it's terribly inefficient. So what we're doing, whether it's fractal antennas, whether it's loop antennas, whether it's PIF antennas, we're enabling a dynamic load to be placed on that antenna, which actually tunes the resonant frequency of that antenna to the frequency of choice.
And I gather this is a MEMS technology.
That's right, and we're using MEMS to do that. MEMS actually has the highest, what's called quality factor, which is really inversely proportional to the power lost in the system, but has the highest quality factor available.
Can you give us a little bit of an overview of how you actually accomplish this?
So we basically take a MEMS technology that's completely compatible with CMOS, and we build what we call switchlets. Switchlets is one capacitor, and it switches either in a max state or min state. We array roughly 500 of those together. So our chip actually has on the order, in reality, of about 1,000 moving parts. And consequently, when they're all up, they're at a min state. When they're all down, they're at a max state. And then we binary weight them to actually go from min to max. So it's truly a digital capacitor, but then it ranges from the min state to the max state based on how many switches are in that one state.
So that's a very interesting way to approach it. So basically it's almost I wouldn't call it a linear scale, but it's a very smooth.
Oh, it's completely linear.
Oh,
In
it is?
fact, if you compare us to D to A converters, or A to D converters, with an INL or DNL, the variability on our LSB is less than 0.15% of the LSB. So
That's a very good figure.
Significantly better performance than even a high-performance A to D.
Offhand, do you know how large your solution is?
Yeah, actually, we're sub 2 square millimeters. Our product is a CSP chip scale package made to go right on the circuit board, and it's well under 2 square millimeters.
Now, obviously, it takes some power to operate this device, even though it's saving power. What kind of power consumption does it?
Yeah, our product is roughly 1.8 volts, runs at 100 microamps, so just a little bit under 2 microwatts.
Oh, okay. And
2
what kind of energy savings do you normally expect, depending on, say, a standard antenna arrangement?
Well, in the low frequency end, we're basically moving the antenna efficiency from the 10 to 15% efficient to the 35% efficiency. So you get the power transmitted, but you also have better receive signal. So then you get better coupling from the antenna into the phone as well when you're getting a receive signal.
And interestingly enough, that would also reduce your thermal problems, wouldn't it?
Yes, it does, for sure. Yes, it does. Because the transmit, actually, you're then not running basically full out on the PAs. And on the receive side, you're able to get your data in and out, and you're not doing a ton of error correction, which is actually what ends up happening, that your bit error rate is fairly poor when you're outside cell area.
Well, Dennis, that's all very interesting, and I think this is very interesting technology. I know that our audience would like to know how they can find out more about it.
So you can go to our website. It's www.cavendish-kinetics.com.
And that's all spelled the way it sounds.
That's all spelled exactly the way it
No
sounds.
funny characters.
No funny characters. Cavendish-kinetics.com.
Excellent. Is there anything else about your technology you wanted to leave with our audience before we closed out the episode?
Well, one of the things that people quiz this all the time on is, what is the reliability of MEMS? It's a big question. In fact, people have been working on these types of products for 30 years. And one of the things that we've been focusing on is ultimate in reliability. And basically, we have the reliability of standard CMOS with our MEMS technology.
Impressive. Well, hey, Dennis, thank you very much for taking the time to be with us.
Thank you very much, Alex.
And I'd like to thank all of you out there for being part of us, because without you, we wouldn't exist. Tell your friends. This is Alex Palt for Palt on Power. Have a great day.
Another promising area of nanoscale technology involves carbon structures, nanotubes, and graphite sheets. Carbon nanotubes have extremely high thermal conductivity, and laboratory devices have been created that use this characteristic to enhance heat removal from transistors and integrated circuits. Arrays of nanotubes expand the heat transfer capacity without degradation, since there is a minimal coupling between adjacent nanotubes. Graphene is the sheet version of single atom thickness carbon. This material also has the nanotube's characteristic of being able to adopt either conductor or semiconductor properties. Extremely small transistors operating in the terahertz range are possible with graphene. The quantum dot logic switches have been demonstrated as well. Demand for communications bandwidth is driving research at even higher frequencies, and graphene is a promising technology for practical devices.
Fujitsu Laboratories exhibited a new carbon composite of nanotubes and graphene at the nano-tech 2009 show. Examples of typical nanotechnology materials include two-dimensional graphene in which carbon atoms are arranged in a planar state, and one-dimensional carbon nanotubes in which graphene is wrapped in a cylindrical wire shape.
Because carbon nanotubes have a one-dimensional structure, they exhibit extremely high conductivity in the vertical direction along the wire. On the other hand, graphene that has a two-dimensional structure exhibits high conductivity in the horizontal direction. along the layer. So if the two structures are combined, we can expect to get a material that is highly conductive in all directions. Until now, it has been difficult to create this type of structure, but in our research, we discovered almost by chance a structure in which carbon nanotubes are connected to graphene.
Applications that are being considered for this new material are applications that can utilize the characteristics of both nanotubes and graphene, particularly the conduction characteristics.
We at Fujitsu and Semiconductor Leading Edge Technologies have joined forces in an attempt to use carbon nanotubes in LSI wiring. In the future, the nanotube section of the structure that is formed when carbon nanotubes and graphene are joined could be used for vertical wiring, while the graphene section could be used in horizontal wiring. We are also considering the use of this structure to convey heat on a three-dimensional level. Another merit of the composite is the flat surface structure. Normally, when carbon nanotubes are grown on a substrate, there is notable variation in the lengths of the nanotubes, and this variation makes it very difficult to connect with other materials. As a result, an additional process is required to cut the nanotubes to equal lengths. In contrast, this new composite material has an extremely flat surface that makes it very easy to join the composite with other types of materials.
Fujitsu intends to develop synthesis technology tailored to specific applications, and also plans to focus on technology that will enable the structure to be freely controlled. DigInfo News.
A final area to note in the nanoscale realm is on-chip optics, which may be the enabling technology for replacement of data buses with the higher speed alternative. The dimensions of today's smallest featured fabrication technologies could rightly be considered part of nanotechnology, but the search for an optimal physical structure for on-chip laser diodes is clearly fits the definition to allow optical communication with the smallest die area and the lowest power consumption. Research in this area involves material on the atomic level.
Don't you hate it when your phone keeps buffering a video or it's slow in loading a web page? Researchers at the Institute of Electromagnetic Fields of ETH Zurich are looking into new ways to make wireless communication speeds faster and faster.
The Internet, as we know it today, is based on a global network of optical fiber cables that connect the entire planet. Those cables have extremely high speeds of hundreds of terabits per second. In practice, this means that each of those cables could carry more than 100 Blu-ray movies in 1 second. However, everyone wants to connect to the Internet wirelessly using their mobile device without using any cables at all. The conversion from fiber to wireless Internet occurs here at the so-called access points. In these access points, the Internet signals that move along the optical fiber are converted to wireless signals that can propagate through the air and reach the users. At the moment, the speed of wireless connections is only 100 megabit per second at best, about 1,000 times lower than that of the fibers. Today, the number of mobile devices is increasing extremely fast over time, and every device is being connected to the Internet, including household appliances, cars, medical equipment, and so on. In this context, the wireless connections are creating a real wireless bottleneck that blocks the increase of connection speeds.
Maurizio and his colleagues are working on novel technologies that bring together the world of photonics and electronics to improve the speed of wireless systems.
Current state-of-the-art wireless systems are built like this. They use discrete components. Some of them convert the optical signals carried by the fibers into electrical signals. Other components amplify these signals, and others transmit them into the air. The conversion from wireless to optical is performed in a similar way. Today, these components are very expensive and are all built separately. This gives additional loss, which in turn reduces the maximum speed.
Maurizio recently received a grant from the National Science Foundation to create novel wireless transceivers that are faster, have new functionality and a lower cost.
The concept is quite simple. We will create novel technology platform by putting together the fastest electronics and the fastest photonics on the same chip. In this way, we can dramatically reduce the cost and increase the speed. This approach is challenging because it requires a strong knowledge of both high-speed electronics and photonics. With this approach, it should be possible to increase the wireless speeds by 100 to 1000 times, making the slow wireless internet a memory of the past.
Summary. Smaller, faster, more capable, and cheaper are the goals for almost all useful electronic devices. To achieve these goals, nanoscale technologies represent the future, whether internal to devices connected by wire or optical fiber to other devices, or as part of the wireless product circuitry. Nanotechnology will play an essential part in the development of new communication options.
We are in the School of Material Science Engineering, Georgia Tech. We have invented new energy technology. I believe they're going to change the world we live in the near future. We look for new energy, but energy is around us everywhere, all the time. But most time we waste them. Until recently, we find this can be a very important effect for energy. Now, how does it work? So what you see here is A materials and B material. When they become physically contact, there's a charge transfer. If they are separated by a gap, there's a voltage generated. The second mode is sliding. If you have two materials, they slide one against the other one. You can also have a charge here. One mode is physical contact, and the other one is sliding. These are the two basic modes we use for electricity generation. This is called trouble electrification, or scientific called contact electrification. And this occurs for almost any materials we know today. Why do we use nanomaterials here? By using nanostructure on the surfaces, we can largely increase the surface area and hugely enhance the charge transfer. Without use the pattern, with use the pattern, the power density is different by 1,000 times. When we first invented this was fall of 2011. The output was just 3 volts. Today, our best can be 10,000 volts. Mechanical energy is everywhere, independent of weather, independent of day or night, independent of season. So anything you can think of, smaller scale from finger tapping, from your touchpad, from the walking to car motion, even train motions, we can do that. We harvest the energy we have been wasted for years. We never use them. So I anticipate this can not only can contribute the power source for portable electronics, but also can contribute power source for large scope of energy need. It can contribute significantly to the worldwide energy need in the near future. And we even think for big ocean wave. Theoretically, let's say 31 terawatt energy can be harvested. That's twice of today's world energy consumption. It will not take too long, 5 years.
Nanotechnology news items. Nanoscale energy harvesting. In the laboratory of Zhongli Wang at the Georgia Institute of Technology, the blinking number on a small LCD signals of the success of a 5-year effort to power conventional electronic devices with nanoscale generators that harvest mechanical energy from the environment using an array of tiny nanowires. In this case, the mechanical energy comes from the compressing a nano generator between two fingers, but it could also come from a heartbeat, the pounding of a hiker's shoe on a trail, the rustling of a shirt, or the vibration of a heavy machine. While these nanogenerators will never produce enough amounts of electricity for conventional purposes, they could be used to power nanoscale and microscale devices, and even recharge pacemakers or consumer electronic devices. Wang's nanogenerators rely on the piezoelectric effect seen in crystalline materials such as zinc oxide, in which an electric charge potential is created when structures made from the material are flexed or compressed. By capturing and combining the charges from millions of these nanoscale zinc oxide wires, Wang and his research team can produce as much as 3 volts and up to 300 nanoamps.
You're watching Keystone Science, and in today's episode we're going to show you how you can get electrical current out of a crystal. First, I'd like to show you guys some objects that you probably have around that utilize the piezoelectric effect. If you don't know what this is a Christmas light fixer. How the Christmas light fixer works is that when I pull the trigger, a little hammer strikes a quartz crystal. The action of striking the quartz crystal creates a high voltage spike. The high voltage spike will be able to overcome the little shunt down there at the bottom of the bulb. This allows a bulb with a broken filament to still allow current to pass through it. Now, another common thing that I'm sure that all of you have interacted with that uses the piezoelectric effect are these. As you can see, whenever I pull the trigger, there's a little spark inside of there. That spark is enough to ignite the gases to therefore light the flame. Now I'm going to go ahead and take this apart so I can show you guys the piezoelectric effect that can generate the flame. Okay, so now we can open it up and see what's inside of this thing. Anyways, let's go ahead and pull this out. As you can see here, there's a little cell with these 2 wires sticking out of it. What happens to ignite the flame with this piezoelectric generator is that the black one is going to be connected to this metal frame that goes up, while the white wire is going to be connected to the line that carries the fuel. And so this way, when you start releasing the fuel, it'll create a spark right up next to it to ignite the flame. Okay, so here I have the generator completely taken out. Now watch these 2 wires when I squeeze the button. As you can see, every time I push down the hammer, a little spark is created. So you're probably wondering to yourself now, why does exerting force onto a crystal make electrical current? A common crystal to use for the piezoelectric effect is quartz. Quartz's chemical formula is SiO2. As you can see, they arrange themselves into a hexagon. Now the silicon atoms have a net positive charge while the oxygens share a net negative charge. Now, keeping in mind with these charges, if the crystal gets pushed in this way, then the shape will more likely resemble this. And the top will have a net positive charge while the bottom will have a net negative charge. Now instead, if I were to take this crystal and pull out on it like this, it would generate more of this shape. Now, based off of this arrangement, the top would have a net negative charge while the bottom would have a net positive charge. And so that's why when the crystal is struck, you can see the quick burst of energy. Now, there are many more uses for the piezoelectric effect. In a previous episode, we showed how you can make your very own speaker, and how the sound was generated by the oscillation of current. This is a piezoelectric buzzer. It uses the exact same principle, except for instead of exerting the mechanical energy, we're giving it electrical energy, and it's giving us the mechanical energy of the vibrations. And so if I take a frequency generator like this one that we made in a previous episode, I can connect it up to the crystal, and now when I flip it on, you can hear the tone as I change the frequencies. Buzzers like this are extremely efficient on their energy usage. In fact, just barely I was giving it less than 10 milliamps. However, the best thing about these piezoelectric buzzers is that unlike speakers, they can vibrate at very high frequencies. And so for that reason, things like ultrasound are done using quartz crystals and the piezoelectric effect. Okay, so here I have the piezoelectric crystal hooked up to my oscilloscope. As you can see, the piezoelectric crystal turns any small vibrations into voltage. Okay, so on this iPad I have a function generator pulled up, and watch how well it follows the wave pattern given off. And so just like that, when we give the crystal an oscillating mechanical energy, it gives us an oscillating electrical current. As you can see, even when I'm giving it a rough square wave pattern, the piezoelectric crystal smooths it out to a nice sinusoidal wave. So now you know what the piezoelectric effect is and some of its applications. Thank you all so much for watching the video.
The earliest zinc oxide nanogenerators used arrays of nanowires grown on the rigid substrate and topped with a metal electrode. Later versions embedded both ends of the nanowires by polymer and produced power by simple flexing. Regardless of the configuration, the devices require careful growth of the nanowire arrays and painstaking assembly. In the latest paper, Wang and his group reported on such simple fabrication techniques. First, they grew arrays of new type of nanowire that has a conical shape. These wires were cut from the growth substrate and placed into an alcohol solution. The solution containing the nanowires were then dripped into a thin metal electrode and a sheet of flexible polymer film. As the alcohol dries, another layer is created. Multiple nanowire polymer layers were built up into a kind of composite using a process that Wang believes could be scaled up to industrial production. Nano-indentation instrumentation. Agilent Technologies Incorporated has announced an innovative nano-indentation technique available exclusively on the Agilent Nano Indenter G200 instrumentation platform. The new technique gives researchers the ability to make substrate-independent measurements on a thin film materials quickly, easily, and confidently by means of nano-indentation. It is the ideal for evaluating the elastic modulus of hard samples on soft substrates or of soft samples on hard substrates. Substrate influence is a common problem when using nano-indentation to evaluate the elastic modulus of thin film materials. The technique is able to extract the film modulus from the measured substrate affected modulus, assuming that the film thickness and substrate modulus are known.
This is Cameron Chai from azonano.com, and I'm speaking to Brian Crawford, who's an applications engineer at Agilent Technologies, and he's going to show us through their Nano Indenter G200.
That's right. This is the Nano Indenter G200, and it's for mechanical testing of small volumes of materials or small devices, thin films, biomaterials. You can see here that we have a sample stage for a variety of test specimens. You mount them simply on pucks. You can test the materials under fluid or just put them down. They're quite easily mounted. A few different things that you'll notice here in this Nano Indenter are the high precision stages that have a step size of 100 nanometers. That's their closed loop linear feedback for position. We also have the coupled indentation heads in here. You'll notice we have the higher force indentation head for indentation up to 500 millinewtons of force. And then we also have the DCM head, which is this black box. And it's for ultra low load, ultra high resolution indentation. The microscope assembly here, it's all fully automated. So you choose the test locations underneath the microscope, and then the samples are automatically translated underneath the indenter tip where the tests are initiated. Over here you'll see the TestWorks interface for the software. And this is your microscope image. We see a couple LCD display devices that will be tested, and everything is controlled directly through the software. So you click and have full mouse control, and it makes this software, makes the platform completely remotely operable. So you can test specimens from your desk or from even at home in your living room. The review page, or the results that you get from nano-indentation, are mechanical properties such as elastic modulus and hardness. Here we see the evolution of the elastic modulus on two different thin film samples. These were low-K dielectrics. And you can see that you're getting properties even down here at 15 and 25 nanometers for elastic modulus. You see a skin effect, and then also the film mechanical properties. Then you start seeing the properties being affected by the substrate, because it's a soft material on a silicon substrate.
All right, Brian, thanks very much for showing us through the nano-indented G200.
You're welcome. Thank you.
Carbon nanotube terahertz polarizer. In 2009, in a 2009 paper, Carbon nanotube terahertz polarizer, researchers from Rice University and Osaka University reported on studies that show strong anisotropic behavior of carbon nanotubes on a film substrate. The lengths that resonate in the terahertz frequency range. The lengths that resonate in the terahertz frequency range, the highly aligned structure was verified by measuring the transmission of terahertz energy through the film. When the signal polarized was aligned with the nanotube structure, absorption was very high. Near zero absorption was observed when the signal and materials were oriented at right angles. The research verified the strong alignment of carbon nanotubes, which has many applications in addition to the polarizer described in the paper.
So what we have here is actually a carbon nanotube forest. So at a nanoscale, they're very tiny, but when we grow enough of them together, we get a very high density of these carbon nanotubes. So it looks like a sort of a fuzzy black mat. When we actually pull on the tip of one of these carbon nanotube bundles, we can pull out a web, and it almost looks like a spider web. And as we twist that web, we can spin it, much like as you'd spin yarn or something. It's just an example of carbon nanotubes. Although they are nanoscale, we're trying to develop ways to make them useful at the large scale. And this is one of the ways to sort of make a cable or rope of a really strong material that's what we'd like. So today my colleagues, Teddy Baker and Dr. Okada, will be showing us how we spin carbon nanotubes in the lab. Teddy's actually attaching a web of carbon nanotubes that he's pulling off this carbon nanotube forest. And he's attaching it to a spinner using double-sided tape. You can see just how sticky carbon nanotubes can be and why they're really difficult to work with if we're talking about large-scale applications. So as he twists the device and pulls away, the web actually spins together. And what we get is a carbon nanotube yarn. And as the carbon nanotubes pull off the forest, they come off almost like a sweater unraveling, pulling off the next carbon nanotube. So even though they're nanoscale, we can actually get a macro-scale yarn out of these materials. And what we'd like to do is make an ultra-strong, say stronger than steel cable out of this material, which is as light as spider webs. So this block of carbon nanotube forest can be spun into about 50 meters worth of carbon nanotube fiber. So right now, although we have a carbon nanotube thread, if we then spun these carbon nanotube threads together, sort of twisting them, we could get a larger and larger fiber. Right now, to sort of make it a little bit more stable, he has to just keep winding it up even tighter. So now he's actually broken the connection from the forest of carbon nanotubes. We're not spinning any new carbon nanotubes, but we're making the thread or the fiber even tighter. And then you can see it's a little bit easier to work with more tension. We're going from carbon nanotubes, which are maybe tens of nanometers in diameter, to a fiber that is 20 micrometers in diameter. So we can keep increasing the size by the spinning process and making useful fibers out of carbon nanotubes.
So I'm holding in my hand a spool of carbon nanotube fibers. So this is a continuous fiber. It's about as thick as a human hair, and it's about 50 meters long on this single spool. So this spool has trillions and trillions of carbon nanotubes that are all aligned in the same direction along the axis of a fiber, and they're very well packed. And because of this structure, we now can translate the amazing properties of carbon nanotubes, which are nanoscale properties. We can now translate it onto an engineering fiber, which is something that we can handle on the macroscopic engineering scale for applications.
So what you're looking at here is 2 bundles of our nanotube fiber that are holding up an LED light bulb that weighs 50 grams. Those fibers are also being used to run the current that's powering the bulb. So this is demonstrating the multifunctionality of the fibers, that they are strong enough to support the weight of the bulb and also have high enough conductivity to provide the current.
This is just some fiber that I took off the drum, which was not under controlled conditions, but it's still good fiber. We don't know exactly what the conditions were, so we don't keep it. But you can see that it has a lot of strength. This thing is actually pretty heavy. This is the spinning cylinder. So we have carbon nanotubes that are dissolved in a solvent, which is chlorosulfonic acid. And this solution is a very viscous type of material, so it's kind of like mayonnaise almost in viscosity. And we're extruding it through 19 small holes and then winding it onto a drum.
This is a spool of the fiber. After it's been spun and wound, this is one continuous filament. So this was produced in a single spinning experiment where we spun a continuous filament and then were able to wind it onto a spool like this. The machine we're sitting near here is the SEM, the scanning electron microscope, and we use this to do high magnification imaging of the surface of our fibers, so we can get an idea of what the structure is on a microscopic scale, the scale of a couple of micrometers or a few nanometers, tens of nanometers.
The cool thing about it is you have a material that's very strong and highly conductive, so it has properties of both metals and high strength materials like carbon fiber. But on the other hand, you can handle it like you would cotton, because it's essentially a textile material, not like a rigid material.
The main improvement that in terms of our process versus other work that's already been done on fabricating nanotube fibers is that if you use a wet spinning process, as we've developed here, you have a very scalable process. So you can easily scale up to make more and more material without necessarily increasing your costs.
So Teiji makes Tvaron, which is one of the commercial brands of PPTA fibers. It's very similar to Kevlar. They're used for high strength applications like ballistic protections. And because the method for making Tvaron is so similar to the method we use for making nanotube fibers, Teijin got interested into working with us. They are real artists in the art of fiber spinning, and they have been able to move the technology so much faster than we could have done just by ourselves.
Graphene-based supercapacitor. Researchers at nano-tech instruments have developed a new graphene-based supercapacitor that can store as NIMH batteries, but charge and discharge in minutes or even seconds. The new device has a specific energy density of 85.6 watts WH per kg at room temperature and 136 WH per kg at 80 degrees Celsius. The problem with the single-layer graphene sheets, according to the team, is that they tend to restack together. They are trying to overcome this problem by developing a strategy to prevent They're trying to overcome this problem by developing a strategy that prevents the graphene sheets from sticking to each other face to face. This can be achieved if curved graphene sheets. This can be achieved if curved graphene sheets are used instead of flat ones.
A lot of times, experiments in science or discoveries look like accidents, but they're only accidents in the sense that we were trying to find something else, and then we realized that what we had was better for a different application. Graphene is a single layer of carbon. It's one of the strongest materials ever known, and it's completely flexible. The discoverers of graphene won the Nobel Prize in 2010. However, the method they used to make it, which was taking graphite and peeling it with Scotch tape, is not practical. So we set out to find a better method. We start with graphite oxide, which is a water dispersible material. We then coat it onto sheets of plastic. We hit it with a light from a laser. Deoxygenates, it turns it into graphene.
So it felt very exciting because we made all organic graphene in a very simple process using a consumer-grade DVD drive that you can find everywhere.
But the real discovery was yet to come. I think the eureka moment that you're looking for was not exactly that. The real exciting discovery came when Maher dragged me into the lab, and he said, "Take a look at this." And he just took a light bulb and he just turned it on with this little piece of graphene. But the amazing thing is, it doesn't stop working. After charging for 2 or 3 seconds, he ran this light for over 5 minutes. I thought we have something very important. I thought the world changed at that point.
Okay, let's talk about the future.
Batteries have a bad reputation, but what we're working on are supercapacitors. And supercapacitors you can think of as a charge storage device like a battery, except it charges and discharges 100 to 1,000 times faster. A battery stores a fair amount of charge, but it charges and discharges slowly. A capacitor puts out a high output, but it doesn't store much charge. So like the flash to a camera. A supercapacitor is one which combines the best attributes of both. If you think about all the electronic devices you have, right now, every time you need one, you realize, oh, I forgot to charge it up. But imagine if you could take that same device, plug it in the wall for 30 seconds or a minute, and be ready to go. Life would be very different. And eventually we'll get to things like electric vehicles. Now you pull into a gas station, well, you'd pull into a charging station, and within a minute it would charge up your car. If you think of batteries, batteries are all composed of a lot of metals, often they're toxic metals. And so in fact, you're not allowed to throw a battery away. But if you had something that's carbon-based, it wouldn't matter. Carbon-based, you could put it in your compost bin and use it to grow vegetables. When I was a kid, I wanted to be a scientist. And so my goal has always been to develop something that will change people's lives.
So truly remarkable stuff. Of course, none of it's is sanctified by any organization anywhere, and so consequently, it's probably illegal to even discuss it this way. But if a human were to take it, then some of these benefits could be anticipated, even though no government saying it's allowed or should be taken. And in fact, you should go into it knowing that C60, which is the residue you could get out of a campfire or off of a match, is also an industrial chemical that they use for lubrication. And so you're consuming an industrial chemical, or giving it to your 6-foot rat to see how long you can make that rat last.
Yeah, no, this message is not approved by the FDA.
There you go. Exactly so.
This is not meant for human consumption.
Right. Only 6-foot rats.
Yeah, exactly. If
Right.
you're willing to experiment. No, I think it's bewildering to think about it. I'm really excited to try the experiment out on myself. Obviously, the best way to do it is to build your own experience and your own understanding of life. It helps with critical thinking. And I'm really interested to see the benefits on someone who's fairly healthy. I'm quite a young man. And again, I think the original way that you're speaking about, the more Ayurvedic sense of that repetitious, slow build-up is probably more functional than that snapback. So to continually take it on a daily basis, at slow doses, you might see these dramatic effects like you're talking about. And again, just to reiterate that because it is an industrial solvent, this is why they were trying to kill the rats with it in the first place, was that it's part of requirements.
It was a lethal dose study.
Yeah. LD50 study on the rats to see how much of this industrial solvent the rats would have to take.
No, it's an industrial lubricant, not a solvent.
Lubricant, sorry. Which I guess would make sense, having that nice round edge of the multi-pointed circle. And
the fact that it doesn't crush.
Oh, you can't crush it.
Because it's molecular. So the wire frame component in an industrial use with lots of the others, they're all rolling together around, and it forms just an amazing lubricant. And it's because the individual atoms don't really crush down. Because of the shape of the soccer ball wire frame being, reinforcing. So it's just really cool, even at that level.
Yes, the world has always managed to blow my mind.
What we've designed, and we've done this very, very quietly, but we're glad to now release it to the world, is this idea of Tesla-phoresis, which is a discovery we made several years ago, and we've been developing it. And Tesla-phoresis is, the simplest way to understand it is self-assembly at a distance, just long-distance assembly of materials. And what we did was, because we're at Rice, we had plenty of nanotubes around, so we decided to use nanotubes. And what we discovered was that these nanotubes can actually string together and form wires by themselves under this electric field.
This fundamental idea of force acting at a distance, that you can have, instead of, when you normally build circuits and things like that, you have to have physical contact. Now we're talking about building circuits without actually touching them.
All right, we're just dispersing this. Power on, and up. I realized that a Tesla coil could actually do this if you designed it in a way to create a very strong force field in front of it. And so that was the engineering aspect of it. And then once I designed the machine, then all sorts of discoveries started falling out of it. Oh, that was a good one!
Tesla-phoresis is one of those things, it's a project that there are just so many avenues, so many things that I think you can do with it. Not just making conductive wires, but taking it in so many different places, not only just biomedical and engineering, but taking it into different industries like silicone chips or exploring different conductive materials.
This also ties in just generally in nanotechnology that self-assembly is very big. That is, if you can get things to build themselves, just as in biology, we build ourselves.
When my son saw it, he called them webs. He thought it was like Spider-Man shooting webs out. And it really is. It's very much like a web sort of stringing out together. And that was a surprising finding. And the physics of that is actually a lot richer than what we had originally thought. So there is new science coming out of this as we go.
Making a few more videos. I'm getting on top of this. Okay, so now let's segue for a minute into health issues. And so I've had health issues relative to what is non-alcoholic fatty liver disease and a potential expression of that as irritable bowel syndrome, which is a very terrible disease. I mean, it sounds ugly, and it is, and it's very debilitating. You lose weight, you lose muscle mass. It's quite painful. You're not going to die, but you think you're going to die. When they did surveys of men and women who suffer from it, over a third of them said that they would be willing to give up 25% of their remaining years of life if they wouldn't be sick anymore. It's that debilitating. I mean, it just robs you of time, it robs you of life. And so I don't have IBS, what I actually have is lectin sensitivity. And I am of the opinion that a lot of the people that suffer from IBS probably are in the same category, where the IBS stuff gets you so far, but you're always touchy, you're always tentative, you're always right on the border of stepping off and getting another attack of the IBS. And this, and the definition of the IBS is such that they're drilling in on a lot of these things that theoretically cause it, but at the same time they're not always effective for people such as myself. And there's this thing called the FODMAP, which is the fermentable oligo monosaccharides and polynols. And FODMAP is actually it's a measurement of short chain sugars that are in various different kinds of food. The theory being with IBS, well, the mechanism with IBS, that what actually causes the pain and everything, is that these particular kinds of sugars, according to the doctors, for causes they can't identify, for reasons they can't state, these particular kinds of sugars make it through your digestion process, which includes the small intestine, and they make it into the large intestine and the bowel, and they ferment, and they cause excruciating pain as the body tries to react to this unexpected fermentation process going on inside it. And it causes all kinds of havoc. It related to leaky gut, is related to bacterial overgrowth. It's related to damage of the ileus, or the ileum, which is the connection between the small intestine and the rest of the system. Leads to all kinds of problems. It can lead to scarring and terrible damage that can be quite debilitating. So it's nothing to mess around with. Now that's IBS as it's described. My issue is with lectins, okay? Now the thing about lectins is they work on a similar mechanistic pathway to causing you the problems. And that similar mechanistic pathway involves proteins called lectins that glom onto the carbohydrates and then take them through the digestive process into the larger gut where they can ferment. So it's still the fermentation, it's still the body reacting to the unexpected fermentation inside it. It's still the body reacting to the problems that this causes, the pain, the bloating, the scarring, the discomfort, etc. But it's theoretically a different mechanism. Now, the doctors can't say, allopathic medicine can't say why people have IBS. They can't say that, well, this particular attack was caused by whatever. They can say that the mechanism that caused it was this fermentation of this carbohydrate. But that's the same thing with lectins.